Bismillahirrahmanirrahim. Assalamu alaikum. In this lecture, we will explore a very important topic in SQL, that is indexes, which is used to find tuples and makes data searching faster. Index on an attribute A of a relation is a data structure that makes it efficient to find those tuples that have a fixed value for attribute A. By fixed, I mean like national IDs, like registration numbers. Sometimes names may be. Any attribute that is able to identify or locate tuples can be used as an index. It is, as I said, a data structure that holds key value pairs. Key is the value of the attribute, and the value is the set of locations of the tuples that have the value of attribute. For example, if I have a relation of students with three attributes, name, gender, and registration number, and I choose to pick registration number as my index attribute, then value of registration number may be 2018 CE10 is the key, and value will be the location where this tuple is placed in the disk. There is a possibility that one or more tuples may be associated with a key. So all the locations will be decoded with the help of key. In this way, if we have the key, then it would be easier to directly jump to the location of the tuples associated with it. Another real life example would be how our home or office etc. addresses are decoded. If we know the street number, then we can jump to set of houses, and if we know the house number, then we can directly access that desired house. Just like in BST tree, we have keys and associated values at nodes. Using key, we can jump to the right or left part of the tree. By bulleting, we can say that in DB, values of the selected attribute, that is index attribute or index key, will serve the key and tuples as values. So there is a mapping. It is interesting that it helps us in searching databases faster. And if we know the key, we can directly jump to the destination. For example, if we do not know the address of someone in particular street, we may have to look up entire set of houses and we will search from door to door until the house is found. Contrary, if we know the address, then we can skip all the search and go to the destination directly. It is to be noted here that index key can be made up of any attribute or set of attributes for a relation. Indexes affect insert, delete, lookup, and update operations. It helps in lookup and searching, but increases cost for insert and delete operations. There are two types of indexes, clustered and non-clustered. At abstract level, clustered means sorted by some attribute, while non-clustered is unsorted data. Index is defined based on its indexing attribute. It can be of following types: primary and secondary index. Primary is a type of clustered index and is defined on an ordered data file. The data file is ordered on a key field, generally primary key of the relation. So it points to complete row, while secondary index may be generated from a field which is a candidate key and has a unique value in every record on a non-key with duplicate values. It's a non-clustered index which just tells us where the data lies. That is, it gives us a list of virtual pointers or references to the location where data is actually stored. In the diagram, you can see that index is defined on the attribute ID, and ID 12 is referring to tuples. Think if it is a primary or a secondary index. We know that searching is much easier and faster in sorted data. Even in unsorted data, if we have proper references or pointers to data tuples, scanning relations is faster. Both clustered or non-clustered indexes provides us with these benefits. Let's suppose that we have books database and there are approximately 7 lakh books in it. We want to search novels written by Garcia. How would DBMS search whole relation? Results might return few tuples, but DBMS need to investigate all 0.7 million books in order to get all the tuples written by the author. With index, let's say on author attribute, a DBMS will immediately check index file where it will find the directions to all the locations and references of books by author Bano Kutsia and eventually get those tuples from disk. Indexes are so important that core indexing ideas are becoming big projects. like when we search Google and it gives us results within a certain fraction of a second with millions of links, and our heart stops and we think, how did this happen? How did Google work on bringing so much related data from a pool of millions and millions of websites? How did it get here? Another example is data blobs in NoSQL. Blobs is actually a collection of binary data. Multimedia objects are sometimes saved as blobs, while NoSQL is another type of database. Actually, with time and growing needs, relational data models were not fitting in certain environments. Data models got evolved as cost of maintaining data decreased. One of them being NoSQL data models. NoSQL databases are non-tabular and can store data in a variety of ways like documents, key values, trees, or graph, etc. They provide flexible schemas and scale easily with large amounts of data and high user loads. Key value stores maps keys to the values. Index is creating on key attribute as shown in the image. Microsoft Azure is running a separate project for blob storage. It provides a key against a blob object and developer can save that key to retrieve its object where it can, which can be any multimedia object like images, etc. SQL Server also provides supports for blob. Let's go through a simple example to understand index. This is an image from Mexico City Public Library. If you want to search for a book, your most obvious design choice will be either to search every aisle or understand librarians' organizing scheme to get proper direction for your book. Let's have a sample algorithm to find our books in library with indexes. To index a book, we have a Dewey Decimal System for the organization of knowledge, and it is being widely used in many countries for indexing. As shown in the image, we have certain digit place, and each digit represents a category, type, or section. For example, as per given example, 7 represents a class among available 10 classes, that is art. 4 represents division in main category. For arts, there may be drawing, decorative arts, or 6 represents section like textile arts. Among digits after decimal places, 4 and 3 gives classification within a section, that is types of textile. And as an example, with ID 66.7 represents 6 as technology class, 3 represents division as in agriculture and related technologies, and 6 represents section, that is animal husbandry, and 7 represents classification or type, that is dog, and if we have 8 then it is cat. For more details, you can go through the link provided in the footer of this slide. So given any indexing system, how will we find our book? First, we need to find the right category of our book. Let's say it's arts. Second, we need to look up index against our category, which will, let's say, tell us the exact location or number or ID of aisle or section number where books for arts will be found. Third, we move to the recorded locations and will search for our book there. It will be helpful if books are sorted by any means, like maybe by name, or there can also be further subdivision like subcategories, etc. We can create indexes on strings and integer attributes. We can also create indexes for time series data, meaning data collected at different instant of time, like sensor data and location services. Similarly, indexes for genomic sequences, that is DNA sequence data, ACCTGA, etc., and video sequences, that is many images or frames coming per second. As for advanced types, we first have to create a problem. We know that currently for any search query, DBMS search in database with exact or equal matching. However, when we are dealing with multimedia type input, like a video, and we want to search an image in database, going for equal matching will not be a good idea. Since video is in continuous motion and most of the time image captured at instant t1 will not be similar to image captured at instant 2. Thus we need to look for such indexing options that brings out data based on similarity, not equality. Similarly, we may also be interested in getting data in certain ranges. We might want to reduce the search space by introduction of ranges. We might also be interested in development of indexes which are helpful in subsequent searching. Interestingly, we can also have indexes which are composite of the above data types. However, it gets a little trickier. Let's suppose we have a company relation with four attributes: company name, stock price, date, and country. We have a query load of two queries. In the first query, all tuples with company name AAPL were asked for, and in the second query, those company names and their data were retrieved whose stock prices were greater than 200. What should be your opinion for the indexed attribute? So we can pick any attribute or set of attributes, but we must look at the query workload first. That is, what kind of queries are coming from users, what type of attributes are being used in searching, etc. So let's say we pick company name as index attribute, as in first query, company name attribute was used for searching. What will happen now? Our index key contains our key and the block number, which is also called a DB block number, where tuples against our company name will be found. For example, if our company name is AAPL, then all references to tuples against AAPL will be saved in our index file. These references are usually addresses, which can be addresses of RAM or of disk if the relation is present on disk. We must also consider here the data is present in the form of pages in RAM, and each page can have a certain size data. We can think that index is a table with first value as key and other as a value. Similarly, we can also have index on price and date attribute collectively, with price and date as key and rest of the tuple reference as value. Let's check another example. We have a relation instructor and we want to search for all the teachers who are working in computer engineering department. If there are 1000 tuples in the instructor table, then without indexes, we will need to scan all the tuples who have the Department of Computer Engineering. For our system, a single page contains 100 tuples, so our table is using 10 pages at least. If we have, let's say, created a non-clustered index on the department name attribute, then we will first check our index file and see for all the references that have the department name computer engineering. So let's say here CE is written and we have references to the tuples which contains the department computer engineering. So after knowing the exact location with CE department, DBMS will directly jump to the locations and load the pages in the RAM. For the example of clustered indexes, we have two relations: product having product ID, name, price, length, width, category ID, manufacturing date and expiry date, etc., and a category table with ID, name, and description as its attributes. So we want to list all the products with expiry date less than 12 April 2020. So do we think that index is required here? So if there are, let's suppose, 10 lakh tuples in the product table, then without indexes, we will need to scan all tuples to get the products with desired expiry date. If we have created a clustered index on expiry date attribute, which means that all of our products are sorted according to the expiry date. If user asks for the product with expiry date less than 12 April 2020, DBMS can easily get tuples as now they are sorted, and thus there might be as few as maybe 10 pages if each page contains 100 tuples. That is, 1000 tuples will be loaded into the RAM instead of the whole relation. So let's solve same example with non-clustered index on expiry date. Assume that we have 1 lakh products and each page contains 100 tuples. It means that complete product relation is saved on at least 1000 pages. So if we have created a non-clustered index on the expiry date attribute, which means that all of our products references are saved against data like hash tables in an index file. If, let's say, user asks for the products with expiry date less than 12 April 2020, then DBMS will check the index file and see for the tuples with search key 2020-0412. There can be 100 such references, and they might be located in worst case scenario in different pages. Like all of these tuples are located on different pages, which means that 100 pages will be loaded into the RAM, although the desired tuples were only 100. Loading of 100 pages means that 10,000 tuples are being loaded into the RAM. So we need to understand that when and what type of indexes are required to be built on our relations, whether they should be a clustered index or a non-clustered index. Our example now involves join of two tables. Suppose we want to list all hardware products with expiry date less than 2020 and category name hardware. So if we have a clustered index on the expiry date, then with this join query, it would be easier if we first get all the tuples with year less than 2020. So maybe there would be 100 such tuples, and then use these 100 tuples to join with the category table instead of joining with 1 lakh tuples of products with category table. If let's say category table also has an index on category name, then we will get one tuple from the category table, and then this one tuple can be joined with the 100 tuples of the product table. Without indexes, we have to look for every tuple in both tables, which is extremely costly. So this slide covers a little advanced topic for the undergrad students, that is how query optimizer joins the relation. So as per Microsoft description on the working of the query optimizer, when a query is executed, the query optimizer evaluates each available method for retrieving the data and selects the most efficient one. So the method may be a simple table scan or maybe scanning one or more indexes if they exist. When performing a table scan, the query optimizer reads all the rows in the table and extracts the rows that meet the criteria of the query. A table scan can generate many disk I/O operations and can be resource intensive. Generally, searching the index is much faster than searching the table because unlike a table, an index frequently contains very few columns or rows, and the rows are in sorted order usually. So, but now the complexity is added with joins. When we have joins, the query optimizer has three options, either to go for the nested join or merge join or maybe hash join. So nested join is just like the double for loops in our programming languages. We have an array in the outer loop, and the inner loop also contains an array, and there exists a direct one-to-one mapping. So for every tuple in R1 will be mapped to the every tuple of R2. So this makes them the nested join. But even for the small number of tuples, it can get really messy because it really costs us a lot in terms of time. So merge join is simply the mapping of two sorted relations. So for example, let's say I have an array 1 which has the attribute 1, 2, 3, and array 2 which has the attribute maybe 1, 3, and 4. So if our relations are sorted on the basis of our join attribute, then I can easily check that this one is equal to this one, and since 2 do not have any mapping, so this 3 will be equal to this one. So sorted arrays or sorted relations help us in having a merge join. So query optimizer can pick the merge join if it knows that the relation contains the clustered index on their join attribute. So similarly for the case of the hash joins, in hash joins we create one hash table. Usually the smaller relation is picked for that, and the other relation is used to probe it with the joined attribute. So since hashing is more cost effective, so hash joins are usually quicker. Query optimizer takes decision based on the availability of the indexes and other certain elements. You can go through the links shared in the reference for more elaboration on the discussed topics. So for this example, possible join choices might be nested loop, merge joins, or hash joins. It depends on certain elements. Even if your query joins more than two tables, SQL Server performs the joins by joining only two inputs at a time. And each join in a query might use a different join strategy, and this is the important point. The most straightforward type of join and the type of join most people think about when planning join operations is the nested loop join. The optimizer most often chooses a nested loop join if one join input is much smaller than the other, and the larger relation has a clustered index on the join column. It means that usually relation with smaller tuples are used in outer loop and larger relation is used inside the loop. With clustered index on the join column, when outer loop is being executed one time, then inner relation's attribute is compared with the attribute of the outer relation. If we have a clustered index inside, then inner loop will be executed quickly, thus increasing the speed of the join. Merge joins will be used when inner and outer relations both have clustered indexes, that is, they are sorted already. So one-to-one mapping will be quick. For hash joins table, usually the smaller of the join result is used to build a hash table on the join key in memory. It then scans the other table in the join, usually the larger one, and probes the hash table for matches. Hash joins can be effective when the lack of a useful index renders nested loop join inefficient. The hash join might be faster than the merge join because only one row source needs to be sorted. And it could possibly be faster than the nested loop join because probing a hash table in memory can be faster than traversing an index. With all this discussion, it can be concluded that Query Optimizer decides to execute the query based on the available information. That is, how many and what kind of indexes are available and what is the size of the relation, etc. After that, it makes its decision. So think in this example, where should be indexes added and what kind of joins will be opted by the Query Optimizer. So how do we add index? Syntax is given. We will use create index, its name, and after on, we will mention the table. And the attribute name will be passed between the small brackets. Here we have selected expiry date to be our clustered index attribute, as the query load shows that users search on the basis of this attribute. And we have also created a non-clustered index on the category name attribute of the category table. Here I have also added a parent category ID in the category table. This actually provides support for subcategories in the application. To drop an index, we will write drop index and name of your index. So here we have deleted our exp date index. So there's also a possibility that we might want to add index to more than one attribute collectively. We can do this by adding them in comma separated fashion. So our name of the index is brand price index. We have created this multi-attribute index because our query load shows that the user searches our database with the brand and price together. So if user searches for the clothes with price less than 5,000 and brand name X, then DBMS will search the index file and see for the brand and price together, and thus reducing the time cost. There are many top important points like B trees and handling of composite indexes, etc., which are left to discuss here. We will explore them in coming lectures. So question here is that should we care about the order of the multi-attribute index? And that is, should we care about which attribute should come first and which should come in second place? So with this example, we can understand this quite easily. That we have a table here named employee with employee ID, first name, last name, age, gender, manager ID, and department ID as its attributes. And we have created an index on the last name and first name, and you should see the order. Last name comes first and the first name comes later. So what happens is, if let's say we try to search the employee table with the last name Gregory, then DBMS will check the index file and see for the last name Gregory and will immediately get the references for all those tuples. So, but for the case of first name, if we try to search only with first name, then DBMS do not have any track. It only knows the last name in sequence. So the example is just like the given in the references. That suppose you have a phone book and you have arranged it with the last name and first name comes afterwards. So if you try to search with the last name, then you can immediately from the index that you will go to the L and see for the you will go for the G and select the Gregory item. But if you are searching the phone book with the first name, then you are stuck. You will need to see all the names, and whenever you will find the first name Billy, only then you can jump to the page number where you can find the record of the Billy. This example was taken from the link which is shown in the references. If our index attribute contains enough attributes that are used in select and where clause, then there is no need to bring all the data to resolve the query. Index alone can be used for providing the results. Just like the example discussed here, we have index on price and date attribute, and the query uses only date and price attribute. So our index alone can answer this query. Such indexes are called covering indexes. So question is now how to select the indexes. Indexes, as discussed, speed up our queries and may be joins involving those index attributes. However, there is a trade-off. Searching is faster, but insert and delete and update operations becomes complex and time-consuming. Can you think of a reason? Since index is a data structure, it needs to save its information somewhere, maybe in files or in disks, to save the key values. When any insert operation is asked, then we will be needing to update the index file as well as the actual relation. Same applies for update and delete operations. So more time is being consumed and more files are now to be updated. So we need to think carefully as a database designer what indexes should we choose and what kind of questions should be in our mind before selection of indexes. Before answering these questions, we may need to understand few key points. That is, that tuples are distributed among many pages and pages are memory blocks. As you can see in the diagram, several blocks or pages are loaded into RAM and we have a relation with some tuples. A single page can hold many tuples as shown in block 1. If you want to read one tuple, then whole block from the main disk will be brought into the RAM and the size of that block can be of several thousand bytes. It means even bringing single tuple from disk can cost a lot in terms of time and space. If the tuple you want to read is already in the RAM, then your time used for bringing page from disk to RAM is saved. You can directly read the tuple from the address you have. If the tuple is not in RAM, then it has to be brought into RAM from disk. So we mostly opt for creating key indexes, that is, we make our primary key attribute our index attribute too, because we know that it uniquely identifies every tuple, and in many cases, user prefers to search the database using the key attribute. For example, we mostly search students table with registration number. We do not search them by name as it can produce many tuples because students can have same names. If in worst case scenario all of our relations are in disk and user searches by key index, then only one page will be brought into the main memory because if user is searching by key, then only one or no tuple will be the result. Actually, index file will also be brought into the RAM to get the location of that tuple and from that particular page containing that tuple will be loaded into RAM. Let's suppose we have a query with joins of two tables, which calculates average price for all products for each category. Since join is involved, product table is joined with category table on the basis of category ID. So all the pages for both products and category tables are required. These pages may be too much to fit in RAM, so some pages will remain on disk while some in RAM. Retrieving from disk can be costly. Even when pages from disk will be loaded into RAM, then some of the pages from RAM should be loaded back to disk to produce space for new pages, and so on until query finishes. Now let's suppose we have a query which gives names of all the expired products in the category of bakery. If we have index on the category name and then only one page containing bakery category information from category table will be loaded in main memory. And with index on expiry date, then few pages from products table with expiry date less than 2020 will be used to join with category page, thus reducing the cost extensively. If we do not have index on category name, then all the pages from the category table must be loaded into main memory to make comparison. Also, without expiry date index, all pages from products table must be loaded into main memory to get list of items who have expiry date less than 2020. So with right set of indexes, query can be optimized. Here we had used non-key indexes.
Non-key indexes can be useful in following scenarios. Point number 1. If attribute does not produces many tuples. If it does, then many pages have to be loaded into RAM, increasing the time cost. Point number 2. If we have clustered or sorted our relation based on that non-key attribute such that tuples are grouped on the basis of the value of the attribute onto as few pages as possible. Summary is that if non-key attribute have the ability to map to few tuples, then it can be a candidate for an index.
So, for example, as for our first case, we have an example where we have student relation having its ID, name, and gender attributes. We have index on its non-key attribute name in students table. Then only few pages with name Ali will be loaded into RAM with the given query. Let's say there are 4 people in database having name Ali and all of them are on 4 different pages. Then these 4 pages will be loaded instead of all pages of students. Still, we are getting an efficiency gain. For our second case, suppose in our product and category example, and query asks for all the product names with the manufacturing year of 2018. Assume first we have index on manufacturing date, but it is not clustered. If there are say 100 products per page, you might have at least one product in a page that has manufacturing date of 2018. If a product relation is present on 100 pages, total 10,000 products, and in worst case all pages have at least one product with manufacturing date of 2018, then we will load all pages in RAM. So even if we have an index on manufacturing date, we saved no time. Now suppose if we have a clustered index on product manufacturing date, that is products are sorted according to their year, then only few pages will be loaded into RAM as per our given query. If there are 200 such products, then only 2 pages will be loaded. So before creating indexes, we need to have some domain knowledge about data to make accurate decisions. It would not be wise to pick any attribute and make it index or make it clustered or non-clustered index. We need to first get some sense out of data. So how do we select best index? We discussed earlier that we need to be conservative about indexes as it increases time taken in insert, delete, and update operations, as one has to update the index file too with the updating of actual relations. Just like relations, index file is stored and saved in the form of pages. Updating index file involves loading index pages into main memory. This means that when modifications dominate in any application, then it would be costly to have indexes. There is a trade-off between search performance and update operations. To select an index, we need to check the cost of query and modifications to relations and of accessing and modifying relations. Only then we can make decisions. The one with lower cost wins. That is, if having index is doing more harm, then depending on the accessing and modifications query ratio, we should not have indexes, and vice versa. We must have domain knowledge before making such decisions. We need to look our query log and see if modifications or access operations dominate. We can also look for history and hope that future will have same kinds of queries, and on the basis of that we can pick index. We can also assume that since maximum types of queries are such and user uses attribute 1 equal to x frequently, and here can treat x as variable and perform our analysis for the selection of indexes. This point will be more clearer in next slide. We can also run brute force, that is picking all possible indexes and evaluating which one is best, or greedy approach, that is picking only those that works best. In this slide, I'm using example from the book of A First Course in Database System by Jenifer Ullman. Suppose we have a stars in relation that contains movie title, year, and star name who performed in the movie. We have 2 access queries and 1 insert query in the query log. Q1 asks for movie title and year for star name S, and Q2 asks for star name given movie name and year. In query 1, we are inserting a new row. In query I, we are inserting a new row in stars in table. We have certain assumptions, that is, stars in occupies 10 pages and it takes about cost equal to 10 for accessing entire relation. On average, a star has appeared in 3 movies and a movie has 3 stars. If no index on star or movie is present, then 10 disk accesses will be required because 10 pages will be loaded into the RAM. One disk access will be used to read index and one for write or modifying index. If we have an index on star name or on the combination of movie year and movie title, then it will take only 3 disk accesses to find the average of 3 tuples for a star or a movie. Insertion as one disk access to read a page where tuple will be placed and one for write. So in point 5, since on average a star appears in 3 movies, so 3 pages, in worst case when all movies are on different pages will be loaded. We will now see if it is better to have no index on star name or on movie name and title or both indexes for the queries Q1, Q2 and I. Let's talk about no index column. That is, if we have no index on our stars in table, then if Q1 is executed, then all 10 pages will be loaded into main memory to get movie title and movie year for the star name S, as we have to check all the tuples for the star name S. Similarly, for the query Q2, we need to check the complete relation for the movie T and year Y, as even our desired tuple can be at the end of all pages. For insertion, cost is 2. Why? Because we only need to access the page where we want to insert the tuple, one for write and one for read. Now if we have index on star name, then for Q1, we know on an average there are 3 movies in which a star has worked. So first we need to access the index page and then 3 other pages will be loaded, which in worst case possible that each page has 1 movie in which star has worked. For Q2, since there is no index on title and year, and search is according to star name, so we need to get all the relation, that is 10 pages into the RAM to get the results. For insert, we need to read and write on index file as well as read and write on actual pages of relations, so it makes total of 1 plus 1 plus 1 equal to 4. If we have index on movie, then for Q1 we need to load all pages to search for star name. So cost is 10. For Q2 cost is 4 because we need to access index file and get 3 pages into RAM. 1 plus 3 equal to 4. For I we need to read and write both index and actual relation, so it's 4. For the case of both indexes, Q1 and Q2 will have a cost of 4 with the same reason of 2 for read and write for index file and 2 for read and write for actual relation. For I, now it is 6. Can you think of a reason? Answer to this question is that now we have 2 index files, so both needs to be updated along with the action relation. So it becomes 2 plus 2 plus 2 equals 6. Since now we have cost measures for all possible types of indexes, how do we decide which index to pick? We might need some kind of average to see if which index attribute gives us lower cost. To get this average, let's make an assumption that fraction of the time we do Q1 is P1 and Q2 is P2, and therefore remaining time we do I, that is 1 minus P1 minus P2. So for no index case, sum of time cost for all possible queries is 10P1 plus 10P2 plus 2 into 1 minus P1 minus P2, which equals 2 plus 8P1 plus 8P2. We will do same for star movie and both indexes column and calculate their sum. We do not need to divide it with 3 as it is just normalization, which do not add much to our measured value. We are getting an idea about our cost with the given expression. Dividing it by 3 will just make our calculations difficult. So let's just replace our calculated values in their respective boxes. So let's come to same question. How should we pick the index attribute? So let's say we do Q1 for 0.1 and P2 for 0.1 fraction of time. It means that most of the time is being spent on insertion queries, and accessing queries are only taking 0.2 fraction of time. That is, maybe 20% of the queries are select queries and 80% are of insertion types. So when we will replace P1 and P2 with their values and calculate average for all four possible types of indexes, then the attributes giving the least cost will be our choice. In this case, we can see that if insertion, that is modifications, are dominating, then we do not need to create any indexes. The case for no index is giving us least cost. Let's change our scenario. Similarly, if P1 is equal to zero point 0.4 and P2 is equal to zero point 0.4, that is, access queries are taking approximately 80% of the time and insert queries are taking 20% of time. So after calculating average values for all the possible indexes, option of both indexes gives a lower cost. So in application where access queries dominate modifications, then it is better to have both indexes. Since Q1 and Q2 are equally distributed, so we need both indexes, that is on star and movies attribute. So far we have discussed that how index will be selected by the database designer, but this process can be automated. Tuning a database is a process that includes not only index selection but choice of many different parameters like number of backups and amount of memory allocation to various processes, etc. Several tools exist for this purpose like AutoAdmin at Microsoft and Smart at IBM. They are built to tune the system itself or give user control to solve issues discussed in point 1. All of the tools have been developed so that system solves its problem on its own. For example, index selection as discussed in this lecture requires to evaluate query workload. This can also be done automatically. User can have certain controls like establish the borders for index selection. Tuning advisor generates a set of all possible candidates and evaluates everyone. Here evaluation means checking with query log what indexes helps in executing queries in least time on average. Resulting index set is presented to the user for final decision, or it is automatically created.